everybody. So I'm back again, and today we're going to be discussing primarily heat engines and refrigerators. I diverged from Fitzpatrick in this series, in this particular discussion of thermodynamics, because Fitzpatrick started talking about the equation of state of the van der Waals gas, which is what we were going to discuss today. However, because he's like, I'm going to do this quantum mechanically instead of, like a sane person and using some other means to derive his formulations, I decided to skip over that because I feel like that's a very large jump in knowledge, and I would need to, fill in a lot of gaps in order to actually show that particular proof, and I don't want to just chuck a whole bunch of, state functions and sums and everything at you guys without you really knowing what the heck I'm talking about. And moreover, I myself need to become familiarized with the material. And because I'm more familiar with this material, it's a little bit more easy for me to describe and teach and so on and so forth. But anyway, so engines. What is an engine? An engine is some machine, which we will usually call M, that extracts some amount of heat from a heat reservoir at temperature 1, does work with that heat, and or transfers that particular, there's some heat loss in the form of, one form or another, that gets put into a second heat reservoir or is lost to somewhere else. Now, engines are thermodynamically incredibly important. If we didn't have engines, we wouldn't have things like, the Industrial Revolution. We wouldn't have vehicles, we wouldn't have airplanes, we wouldn't have rocket ships, we wouldn't have quite literally anything that we see now in the modern world that came as a consequence of the Industrial Revolution. So it's also, historically, we see a lot of studies of engines coming forth in that era of the, Industrial Revolution and so forth. And we actually get a lot of our thermodynamics expressly because of this particular phenomena. So to begin, we always like to talk with an ideal case, right? And our ideal case would be that of a perfect engine. A perfect engine would apply the same amount of work as the amount of heat that it would extract from a particular reservoir. Oop, my iPad's kind of shaking right now. I'm not up by the whiteboard for this video right now because it's a lot of text and I need to narrate some things to kind of give an intro. But besides the point, like I said, an ideal engine would take all of the work from, or would have taken all of the heat that it gets from some reservoir, and it would completely and totally imperfectly convert that amount of heat to some amount of work, right? But that's not necessarily thermodynamically possible, and we'll get into that a little bit later. There are some caveats that we do need to know about our engines, right? So namely, our work that the engine, the work that the engine itself does should not be provided at the expense of the heat engine itself. So if basically heat should not be extracted from the engine when it is doing work, at least for the perfect or idealized engine. Otherwise, you can't get that particular engine to return to that same initial macro state, because then it would have less heat than what it started with, and that would be a violation of, I believe, the second law and the first law. Yeah. And secondly, the work that the engine does needs to change some external parameter without affecting the entropy of the object in consideration. So essentially, whenever the work of the engine is done onto some system, that outside external parameter of that system has to change, but the overall state function of the entropy can't change, at least once again for the idealized case. So once again, those are two primary caveats to our engine question. And with these two particular caveats, Rife asks a second longer question, and I'm just going to read it out. This is on page 185 if you have the textbook. It's sitting right in front. Right there. There's the textbook. To what extent is it possible to extract a net amount of energy from one or more reservoirs where that energy is randomly distributed over many degrees of freedom so as to transform it into energy associated with a single degree of freedom connected to an external parameter of an outside device? That's a whole lot of unpacking to do. It's a very long statement. Essentially, we want to see if we can get our engine hooked up to multiple heat reservoirs, extract from all those heat reservoirs some amount of heat, Q, and transform it into some sort of associated energy, changing and affecting only the single degree of freedom of a single parameter of some device in question, right? So let's say, for example, we have an engine, it's doing work, and we want this engine in particular to increase the volume of some other thing. And we only want to make sure that this engine only does work as to affect the volume parameter. I'm using this as an example. I don't know if that might be the case with actual engines. I can't think of any off the top of my head, but that's the question that we're essentially asking. So after a single cycle of doing work, our idealized engine should return to the same original macro state that it started with that caveat in question that it doesn't lose heat at the expense of doing its work. So by the first law, we would have that the work done is equal to the heat that is extracted. And now we're going to get into a few of the issues here, and then even go on and talk about some of the math behind it, and then explore refrigeration. So I might have said off, like as an off comment, that an ideal engine violates the second law of thermodynamics. And that's because it quite literally does. And Rife spends the next couple of pages just kind of discussing why that's the case. So he requires that for some ideal engine, for a single cycle, that the change in entropy of that particular engine has to be greater than or equal to 0. However, there isn't any sort of entropy change associated with the object that our machine does work on. So from the diagram that we've got above, if we don't consider the second reservoir, we just have the machine's output of work is equal to the negative amount of heat extracted from that particular first reservoir, right? And if we know that that's equal to the amount of work that we have, and that's negative, then the amount of work that we do, that the machine does, or the engine does, is less than or equal to 0 whenever we, get rid of that negative sign. In other words, you would have negative work, and we can't have an object that's doing work produce a negative output, or otherwise we don't have an engine. So for that reason, an idealized engine violates the second law of thermodynamics, right? More expressly, he kind of elaborates too about the implications. Oop, my camera's slipping. He also elaborates on the implications of these particular processes that an engine will do. So nobody's really objecting to the fact that some amount of work can be converted into heat. However, the heat itself for an engine cannot be converted into work, for an ideal engine at least. So what this says is that the process that an engine does, unless it is hooked up to some other reservoir, T2, is in effect an irreversible process. So if you have a piston and you pump the piston one time, the macro state of that system can never be returned to the initial state that you did before that cycle transpired. Now, statistically, is it possible? Yes. Is it probable? Fantastically, no. Those are the words that Rife uses. He says it is fantastically improbable that such a thing would happen, to the extent that we just say that it won't. So if we have some sort of process that's irreversible, how do we account for the second law violation? Well, we'd have to account for some sort of decrease in entropy of the overall system, right? Because we get that negative work statement. Now, this is only possible if the engine itself doesn't exist in isolation. So we introduce that second reservoir into which we get a heat transfer of Q2 to temperature 2 in that reservoir, such that the temperature of the second reservoir is lower than that of the first that it's extracting. When we consider that reservoir in our change in entropy calculations, what we can do is that we can write our change in entropy as the sum of the negative heat lost from that first reservoir into the plus of the heat gained by the second one, divided by the respective temperatures, all equal to 0. We know that we can rewrite the heat gained by that second reservoir Q2 in terms of the heat lost Q1 and the work done by the machine itself. So we plug that in, and then we can solve for work here. And when we solve for work in this inequality, we can actually reorganize that a wee bit more. Rife shows some intermediate steps. And we can actually get a ratio of work to the first amount of heat lost, Q1, by that first reservoir. This particular ratio is less than or equal to 1 minus the temperature of the second reservoir divided by the first reservoir. And then you can rewrite that as an overall fraction of T1 minus T2 divided by T1 if you want to do that math. But we get another constant, also aptly named eta, because Fitzpatrick and Rife decided to use slightly different naming protocols, or I don't know the verbiage for that, but Rife adopts the term eta for the efficiency of an engine, a real engine, right? So for a real engine, this particular quantity can just simply be written as the ratio of the work that is done by the machine or by the engine divided by the amount of heat that it pulls from the first reservoir. And this number will, in general, for really most engines, or really all engines that are real, will be less than 1. Now, for an ideal engine, this quantity will be always equal to 1, but obviously that's not attainable, so we usually don't really worry about that particular calculation unless we're doing some sort of theoretical calculation to see if the engine we made is or isn't accidentally an ideal engine, right? But yeah, those are engines. And that's an overall review of engines and the difference between an idealized engine and how we make up for that violation of the second law, and we actually wind up with real engines, and we're able to describe these engines in terms of their efficiency and their temperature and the heat that's gained and lost and the amount of work that they do. Now, with that in mind, we can now turn our attentions finally to refrigerators. So last but not least, we have refrigerators, right? So the fun thing about a refrigerator is that a refrigerator is quite literally an engine in reverse. Now, when I said we couldn't have negative work happening for an engine, this is what I mean. Because an engine would increase the heat of the system that it is being applied to. We get the exact opposite whenever we have a refrigerator. Why? Because a refrigerator has work done on it, and it extracts heat from the reservoir of lower temperature and takes it to a reservoir of higher temperature. So like think of your average freezer on your refrigerator. It takes heat from inside of it and it throws it outside so that the inside of that particular freezer can stay cold, right? That's a refrigerator. There's refrigeration happening inside of your freezer. Now, like I said, just to reiterate, our refrigerator takes heat from a reservoir that's at a lower temperature, and it rejects, that's the word that Rife uses, rejects that quantity of heat onto another reservoir with some higher temperature. And yeah, once again, I reiterate, that's why it would be the opposite of an engine. So similar to an engine that has some sort of idealized state, we can also have an idealized refrigerator. Now, an idealized refrigerator would be able to take the amount of heat from the lower reservoir and transfer it to the reservoir with higher temperature without needing to do any sort of, or without having to need work be done on it, right? So when we throw that into entropy considerations, namely the second law, which requires that the change in entropy always be greater than or equal to 0, we actually witness the same kind of entropy violation, right? So if we take this into consideration, we don't look at work whatsoever, we notice that for an idealized refrigerator, the change in entropy is equal to some amount of heat, Q, being added to the higher temperature reservoir minus that same amount of heat from the second lower temperature reservoir. We set that equal to 0, and then we can factor out our Q. The issue is that this particular quantity doesn't hold for values of Q that are greater than 0, nor does it hold for values that say that the temperature 1 ought to be greater than temperature 2. This particular statement is known as the Clausius formulation of the second law of thermodynamics. The previous statement regarding the idealized engines not being able to exist is known as the Kelvin formulation of the second law. But not the Kelvin, the Kelvin. My gosh. I've been folding socks and I have some Calvin Klein socks. It's written very nicely on the embroidery, so I've got that going through my brain. So it happens when you do laundry all day and then you try and talk about things. Anyway, with that in mind, we actually do have to consider work when looking at our real refrigerators. And when we do consider the amount of work being done onto our refrigerator and we reparameterize the heat that is being taken from the lower temperature reservoir, then the math begins to math, right? So we have our change in entropy is equal to our heat from the higher temperature reservoir divided by the actual temperature of said reservoir minus the heat lost from the lower temperature reservoir divided by the temperature of that reservoir is greater than or equal to 0. And when we take a ratio of the heats to the ratio of the temperatures, which is what we can do, we notice that these ratio of heats are always going to be less than or equal to the ratio of the temperatures of the two reservoirs. And that's important because this particular equality would hold only for some quasi-static processes, which means that refrigeration is typically a pretty slow process. If we want to look at it in particular, I think that Rife outlines that refrigeration in this context can be looked at as being the reverse or the quasi-static reverse process of some Carnot engine. And if I have time, I'll make a video on a Carnot engine and what those are and how they operate. But for now, it's just consider a regular engine. But yeah, similarly, the efficiency of some refrigerators are also going to be less than 1. It's never going to be equal to 1 unless you're an idealized refrigerator. But you're always going to have some amount of work being subtracted from that quantity of the initial heat. Or not necessarily the initial heat, the heat from the first reservoir, T1. So with that in mind, we can show that a real refrigerator does not violate the second law of thermodynamics, but an idealized one does. And we can also see that refrigerators are, thermodynamically speaking, just the exact opposite of an engine.